Yeah, coffee's a good thing for this morning.
Yep.
Evening, everyone. So, respected participants are very welcome to GMA webinar. We are privileged to have among us Mr. Eric Yandell from Applied Material Solution as the speaker from industry. Mr. Eric is account manager at Applied Material Solutions with the more than 25 years of experience in industrial chemistry, including 12 years in the ethanol industry. He holds a BS in chemistry with Western University, MS in chemistry from University of Alabama, and an MBA from University of Louisville. Eric's background spans water treatment, waste treatment equipment manufacturing, and specialty chemical solution, where he combines strong technical expertise with strategic accounts management. His areas of strength include problem solving, statistical analysis, and applying scientific principles to improve process performance and customers' outcomes. He is the holder of US Patent, a two-time Pinnacle Sales Award recipient at Beckman, and a long-time member of American Chemical Society, currently serving as chair of the Prudhoe local section. I would now like to invite our knowledge partner to start knowledge share. So over to you, Mr. Eric.
Good afternoon, everyone. I appreciate the introduction. Very nice. Appreciate the ability to be here today. Let me get my slideshow going. Okay, does that look right to everyone?
Yes, Eric.
Thank you very much. Okay, yes, I am with AMS. We make demulsifiers for the corn oil industry here in the United States, along with other products. A little background about us. We were formed in 2015 by acquisition, mergering, if you will, several smaller companies which specialized in silica production, modification, and then defoamers. It makes us basic manufacturers and a lot of these defoamer type products. Currently, in the fuel ethanol market here in the United States, we produce a little more than 1.5 million metric tons per year of demulsifiers, and we're in about 85 ethanol plants here, which is about approaching 50% of the plants that we have in current operation here in the United States. In addition to our corn oil demulsifiers, we manufacture, like I said, products for antifoam, defoam, and other process additives for wastewater, water treatment, food processing, pulp and paper, and paints and coatings. A number of our products can be used in paints and coatings for rheology modification, for durability, things like that to improve the coatings of things. We have 3 manufacturing sites. Elkhorn, Wisconsin is our corporate headquarters. It's where we make a lot of our food grade defoamers and other food grade products. The home of our R&D lab as well. Burlington is where most of our corn oil demulsifiers and products are made, as well as our colloidal silica and other treated silica products. Rockton, Illinois is a fairly large facility for a lot of our toll manufacturing business and a lot of warehouse space. Currently, we're equipping it with a little more equipment right now. Yeah. So to get into what we're going to discuss today, which is our corn oil products. Yields here in the United States are typically expressed as yield per bushel of corn ground. A bushel of corn, of course, is an old school imperial unit, about 25 kilograms. and each bushel contains about 0.9 kilogram of oil. It's just under 4% oil here, about 3.6, 3.7. It's mostly located in the germ. So on a theoretical basis, 1,000 kiloliter per day plant would have the opportunity, or at least the theoretical limit would be not, just over 90,000 kilograms of oil per day. Actual yields are in the roughly half to 65% of that. 65% is doing pretty well. Here in the United States, if we are able to extract about, of course, we work in pounds. If we were extract about 1.3 pounds per bushel, we're at about 60%. So some of our top end, more toward the top end of the plants, we're at about 60% recovery of the theoretical currently. There's some more equipment coming in that can kind of help work with that, but that's probably another presentation. The things that really impact the oil recovery that we see, the largest ones, is particle size. Most of our mills are dry mills, which is a hammer mill or a roller mill type of process. There's other additives, not additives, but other equipment that they've added to this, like the FST and SMT, which is fiber separation technology and select milling technology. It's the technologies that are there to help access the starch for the most part, just for better fermentation. The fiber separation removes a little bit of solids, unfermentable solids, prior to fermentation, which helps with fermentation yields and oil yields. And then select milling is in there to help particle size distribution. Generally, the smaller the particle, the better for oil access and starch access from what we see. I'm sure you folks also see that. The solids concentration in liquefaction and slurry also fairly important for getting the most out of your fermentation and recovering the most oil. The more fresh corn, maize you can put into a fermentation, the more oil you have available per batch.
Eric,
Yes.
sorry to interrupt you. Can you just zoom in the slide a little bit if it's possible?
Zoom in.
Uh,
It's a good question.
if it's possible.
Where would that be, Anand?
You'll have to go out and again then start sharing, I think. Go out and then again come into presentation mode.
Sir, on the right hand side, there is an option of slides. So please click on that.
Let's continue. Okay, let's continue.
Optional slides.
Rekha ji, that three
I think it's
little
totally
dots.
fine. I think it's totally fine.
Okay.
Yeah, sir, please
Yeah.
continue. It's fine. Sorry for
Fine?
the
Okay.
interruption. Please continue.
Okay. Now I've done lost my. Oh, there we are. Okay. All right, back to here. Okay. So yeah, solid concentrations, more per batch. It doesn't necessarily mean your yield per kilogram of maize ground improves. It's just you get more through the plant. And then in a large part, which we don't typically get too involved in, is the enzyme packages. Those seem to have a fairly decent impact on oil recovery, positive and negative, sometimes depending upon how experimental the enzymes are. So the first step, what we normally see in the spent wash, we call whole stillage. It's just post distillation. Typically that process stream goes to a set of decanters, which are vertical centrifuges, separate the spent wash into a wet cake, which then goes on to a set of dryers typically. And the liquids, then stillage, backset, all of that, depending on what you do with it. This is the first loss that we see in the plants, and I'm sure you guys are all aware of that, that any oil that leaves with this wet cake fraction is just unavailable to capture later. So currently there's equipment, we have products for this application point to try to pitch more oil toward the liquid fraction here, which makes it then available to capture at least later. There are some mechanical adjustments here that you can do, whether it be adjust the torque or the flow or things like that on these decanters. Frequently, you can pitch a little bit more one way or the other. You know, monitoring the amount of oil going out is pretty important at that point, I believe. And then the thin stillage, which comes back around into evaporation, it gets that high temperatures and retention time in the evaporators. That typically helps bring the oil droplets together, making them larger, easier to recover. And then here, at least, we draw off a syrup or a thick stillage type sample to run through oil separators at the last stages of evaporation. Whatever your evaporator setup looks like, there's a few different configurations here as well. And then that de-oiled syrup is then returned to the process to mix back in with the wet cake and goes out as Distillers dry grain here. The types of oil separators that we see over here most commonly are your disc stack, sometimes called high-speed separators. They have a fairly, well, relatively lower capital cost investment, typically a smaller footprint, and they make a two-phase separation. They do a fairly decent job. They're fairly easy to understand. I'm sure you guys have seen a lot of these. I know I've seen a couple of webinars from the equipment manufacturers, so I know how well versed you guys are. The other ones we see most commonly are the tricanners, the vertical, horizontal ones that actually they make a three-phase separation, which is oil phase, a light phase, a water phase, if you will, and then a solid phase. Typically, the solids and water phase are somewhat immediately recombined so that you don't really notice that it's making a three-phase separation, but you get oil back. The benefits, the pros and cons here to these guys are the disc stacks seem to be slightly lower capital cost. The tricanners seem to operate over a slightly larger solid concentration. They're a little less sensitive to solids and flow consideration. So this is our general map of the way our plants are laid out, and these numbers are from our own internal AMS database. We collect a lot of process samples to help our customers troubleshoot various things. So we record a lot of these solids by weight, just how many solids, per volume you have. And then to compare across plants and different sample points, we use this normalized fat constant calculation, which is just the grams of fat in the sample divided by the grams of dry solid in the sample. And that gives us more or less a number we can compare plants to plants with some, reasonable amount of comparison. And so these numbers actually come from our own database. Like whole stillage normally runs, or spent wash runs about 12.5% solid and about 16.5% normalized fat. So as you can see, our first split here, about 10% normalized fat leaves without us being able to get it. That equates to, half or ish of the amount of oil available totally in the corn or maize. If we can pitch more toward the liquids fraction, to head over to Centrate to be used as backset for thin stillage to track the normalized fat here to kind of capture how well we're getting fat recovery throughout the system. In this particular one, we have a distack represented. It could be a tricanner. We have Distillers corn oil storage, and then the de-oiled heavy phase. On average, our de-oiled heavy phases are about 3.2% fat remaining. So we're still capturing like 92% of the fat going to the distack or tricanner. And that's typically what we see. If the oil makes it here, the oil separation equipment usually gets about 90% on average of the oil that comes to it. So we have a product or two available in India. It's a fairly robust product. We're working on getting more approved for usage. When you're screening your product, we recommend that you use several dosage levels and repeat it several times. The key here is to grab hot, fresh substrate whenever you can for every dosage round. If you allow the stillage or whatever to cool off, it really very quickly impacts the results of your testing. By testing at different dosage levels, you kind of get an indication as to where your dosage is going to wind up in the plant. That's not to say that it's going to equate 1-to-1 exactly. Bench testing seems to overpredict the dosage needed by a little bit. So you probably, in other words, if your dosage says you need 200 parts per million, you may be 180, 150 parts per million in application. Demulsification at the spent wash. We have several products online here in the States for this. Currently, it's a big deal here now. Slightly different mechanism. If you think about the end of evaporation, the thick stillage or syrup application, you're really looking to make smaller oil droplets large for the oil separation equipment to remove them. Up at the spent wash location, where you're going into a decanter, you're really just looking to get the solids that are loosely bound, so to speak, or loosely associated with the solids into the liquid phase. So we have slightly different formulations for that to do the lifting of the oil off of the solids to get it into the centrate. Again, if you're going to screen at this location, hot, fresh substrate should be grabbed each time, and then several replications, and over the course of a few days to help determine which product is the most robust for that application. And then there's a lot of discussion these days about the correct injection point for demulsifiers, both at the syrup and spent wash locations. And from our experience, it really depends upon the plant layout and how your process is running. Some places really do require as much retention time and mixing as possible for the best oil recovery, and some places do not. There's the opportunity with these applications to basically do good work and make nice big oil droplets or liberate oil from the surface of solids, and then re-emulsify it with too much mixing, depending upon the pumping situation and the layout at your plant. And I've seen that at plants and shown customers that, injection here and going through these 3 pumps just shears everything up, and you've really undone all of the good work that you did to make nice recoverable oil. So what prevents us from recovering the oil in the first place is, natural surfactants that are occurring in your maize and and other feedstock grains is likely weren't things intended to be surfactants, but after you digested them and treated them with enzymes, they sort of act that way. It's generally just a polar head with a hydrophobic tail, so to speak. In this particular instance, I used positives. I got to thinking about this yesterday. I think most of them may be negative in the actual maize applications, but the principle applies. So you have these hydrophobic tails with a nice charged head on the outside, stabilizing a drop of oil. It bumps into another drop of oil, and these positive charges, naturally repel each other. A primary mechanism action of our demulsifiers is to prevent this particular thing from happening. So our demulsifiers are, mostly hydrophilic tail and a hydrophilic head that's not charged. So when the two oil droplets come in close proximity, these areas don't repel each other, but allow for much closer contact, and then the two oil droplets can merge and become a much larger oil droplet for separation into centrifuges, whether those be Distax or Triton. One of the things that we do, which I'm sure you guys do similar, is to test and examine various parts of the process on the way to oil separation. A lot of plants here grabbing centrifuge tubes and spinning things down is a pretty common practice, both on finished oil for quality and for other process points along the way. We typically also do some microscope evaluation where we'll use, transfer pipettes to transfer a small drop of various process streams, put it under the microscope for examination. So that way you can see how big your oil droplets are. It's a qualitative measure, but it's good to do when oil production is good. That way you know what good looks like in your process. And if something goes wrong and oil production drops off, you can go back to the same key process point and look and see if it's going wrong all the way back to spent wash, or if it's something to do with maybe an intermediate step in evaporation or something of that type. Then for the testing of the product at dosage levels and stuff like that, you need a micro pipette with positive displacement plungers. This gets to be a little tricky. I have a model number I can recommend to you guys if you don't have them already, which will accurately dispense the viscous corn oil demulsifiers down to about 3 microliters, which makes it nice to test in the 50 mil centrifuge tubes at various parts per million in the relevant parts per million range. The key locations that we like to monitor these are ahead of evaporation, so typically in that thin stillage process stream, just to see how the oil droplets look then and there. The dose feed right at the oil separation equipment. Usually there are sample points fairly close to the inlet of those to make sure that it looks right, that you're still getting a good break of clean oil versus the water phase. We like to check the defatted stillage, the heavy phase out of the tricanters or Distax, to make sure we can't see any free oil in there, and that's with spins and with the microscope. And then post evaporator pre-dosage, that gives you some indication as to what it looks like coming out of your evaporation system before you hit it with any demulsifiers. That would give you the indication that something's mixing or some sort of thing is going on in your evaporator system that's messing up your oil recovery. And then most places monitor their oil quality on a fairly regular basis to make sure it's meeting specs for their customers. So I'm sure a lot of you already do a spin test at various points. Those are good to do both when things are running fine and when things are upset. We like to make sure we do the microscope evaluation. And not a lot of our customers seem to do this on a fairly regular basis, but we will do this when we're in there with them just to sort of document how the process looks at that time. And then if something goes wrong, we can go back and look at previous photographs and things that we've taken for that. And then dosage profiling, both with your existing product and any new products that may be in the market, is good to do periodically. Usually, if you have like a feedstock change, like you're including more rice or more other grains, it's a new crop of corn, if you've made any significant change to your any significant change to your enzyme package or fermentation, like a yeast or something like that, it's good to go back and reevaluate to make sure that you're still in the right product and or product dosage range for after the change. Keeps your process engineers busy. So spin testing, this is typically what we will see at places as a basic monitoring tool. We'll collect the dosed feed right before the oil separation, make sure we're getting a nice clean break of oil, and ideally with as little of an emulsion layer below the oil as possible. This one is a fairly good one. There's hardly any emulsion here. That's not to say that some emulsion isn't expected. Most places have a little bit. And then when you spin down your heavy phase, this is what you want to see. You don't want to see any free oil. You don't want to see any, or as little as possible, emulsified oil. You want all that to come out with your light phase and go into product. Under the microscope, what this looks like is you'll see these nice big oil droplets in the feed. All of these pretty much are capturable. Some of these tinier ones, if you really want to zoom in on the photos, may not be capturable, but for the most part, most of the oil separation equipment that we see here in the States will grab pretty much all this, as can be seen here by just no visible oil in the heavy phase, which is good to do. I like looking at this heavy phase under the microscope to make sure, just because the spin sometimes can be a little misleading. Like if you see some of this flaky stuff here under the microscope, that may show up as capturable oil if there's a mechanical issue or some other problem with the oil separator. More examples from other plants, sort of your end of evaporation process stream will look like this without demulsifier dosage. It'll have emulsified oil, water, with a little bit of particulate matter built, kind of built in there to that. This sort of lumpy, emulsion. The dosed feed breaks out the oil. This particular plant has a little bit remaining of the emulsified oil. Some of that probably also captured by the oil separator. What that looks like in principle under the microscope is you'll have this, oil is visible. It's slightly smaller droplets. After you dose it, it becomes much larger, much easier for the oil separator to capture. And you want to make sure that you see this sort of thing. What we see sometimes here too is you can detect an overdosage situation. If these oil droplets are super large and misshapen, not these nice spheres like you see here, but sort of a misshapen glob. That may be an overdosage situation. You may want to adjust your dosage down, give it a few minutes, and then resample to see if you've improved the structure and coalescence of those oil droplets. So typical heavy phases here too from one of the distack units is seen here. So this is a place that has two distacks in parallel. Distack A, or PCOS A as it's referred to, you can see is fairly clean. There's some solids, but no real visible oil. You may need to zoom in on this a little bit at some point, but TCOS B, the heavy stack or heavy phase from B, has some noticeable oil in it. They're very tiny, but they are there. And so this would be the instance where you could maybe make mechanical adjustments to the machine, or it may be that on your next shutdown or planned preventative maintenance shutdown to put this on the list of equipment to inspect and possibly repair, because there may be something letting the light phase pass extractor and into that heavy phase.
Hey, Eric, can I make a real quick point on that?
Sure, go ahead.
Um, when when you're taking samples of the heavy phase, guys, um, on a specifically on a disc stack centrifuge, you know how you set your chutes at certain intervals to blow the solids out of that machine and clean it. Typically, around somewhere between 2.5 and 6 minutes. It's important to take that heavy phase sample um, at the right interval after it does the shoot. So if you're doing 4-minute shoots, you want to take the sample at about 3 minutes after it does the shoot, because if you take it too soon, um, that sample will really look like garbage after a shoot on one of those disc stack centrifuges. So that's just something to know going forward if you're looking at that.
Yeah, that's true. That's a good point to make, because we try to collect all of ours, like Rick says, about that mid shoot time so that we don't crowd the shoot one way or the other. So when you're doing dosage profiles and or product selection, we recommend, like I said, you start with hot, fresh, syrup, spent wash, whatever you're doing every time, and compare basically just within that one collection point. The process changes a little bit, so comparing sample grab to sample grab maybe will be tricky, but you can certainly sort of rate them in order. Like in this one, you would say 805 is maybe the best, 411 here, this next product is maybe the worst. On your next replicate, if that maintains the same order, then you're closer to selecting, the most robust product for your particular process and plant at that time. Same way with the dosage profiles. If 250 parts per million looks better than 200 or 300, then 2 or 3 times in a row, then you probably can start at about 250 parts per million and be confident that you're in the right range for dosage. For our dosing equipment, we have found that positive displacement pumps tend to work best. These products are fairly viscous, 1,000 to 3,500 centipoise. They don't like to get cold, obviously. Positive displacement pumps seem to be the most robust and most linear. This is a photo of one of our chemical skids or dosing skids that we build and sell to customers here in the United States. Key to have a drawdown cylinder, I think, so that you confirm your dosage rate to make sure that you're dosing about the right amount. Positive displacement pumps really do not like to be deadheaded. So on all of our skids, and I recommend on all of yours, if you have a positive displacement pump, you have a pressure relief valve. That prevents it from being deadheaded, whether somebody accidentally shuts a discharge valve or a valve further downstream, closer to the injection point. This will recycle the flow to the suction, and you won't deadhead your pump and kill it in just a few minutes. Also, if you just run poly tubing from the discharge to the injection point, your poly tubing will be a pressure relief valve, as if something plugs up or whatever, then it'll pop the tubing, and you'll notice that too. Don't recommend that, but it is an option. So on our skids, we have the suction here valve, kind of valved right in, so that we can then shut off the base tote or drum and then do a drawdown to confirm If you're in a deadhead situation, like your line is plugged or whatever, when you do your drawdown, you'll notice that it just doesn't draw down. So that'll tell you something's plugged in the line. For our injections, we commonly will recommend injection quill. This is mostly in the discharge of pumps or in applications where the mixing time is not is fairly limited. In other words, if you're injecting in the discharge of a pump and that's the pump that feeds your oil separation equipment, so you only have, say 30 meters of mixing pipe, we would recommend an injection quill. It gets the product dispersed more quickly and better so that it has better efficacy. In the suctions of pumps, for the most part, that we've seen on spent wash, thick stillage, syrup applications, it's typically violent enough, moving enough, and it goes right before the impeller that we don't normally need an injection quill on the suction of a pump. Just normally, I think that it seems to work pretty well with the mixing of the centrifugal pump in there, as long as they're not over sharing it, like if you're going through multiple centrifugal pumps. Business cases here may lean on our partners Adita for going through this, as they're more familiar with the units, but I did double check all these numbers and it seems to be very close to what we see here in the United States. So I don't know if Anand is on, can talk through this.
No, Eric, you can continue. No problem.
Okay, thank you.
Yeah.
So what we see normally is the paybacks for most of these applications are in the month, especially at current oil market prices. I think most of these work out to be typical of what you guys are seeing as far as what you invest for the dosing system and any bulk tanks or otherwise retention tanks and piping. And then the selling price of 105 rupees per kilogram. And then the cost of the demulsifier, which can be, you always want to figure in the cost of your demulsifier for paying for itself. You don't want to just make oil for the sake of making oil. It costs you money. Typically what we see is in this range, 140, 150-ish parts per million up to about 250 parts per million in the syrup or thick stillage dosage point. For the spent wash, it's more dilute system, more dilute process stream. Typically our dosage there is down around 100, 75 to 100 parts per million in a lot of applications. Some of them drift up to 150 or 200 parts per million in spent wash applications, but not many. I would expect the same would be for you guys. The mixed grain applications get a little bit trickier. We do not have a lot of experience here in the United States with mixing in rice. We have experience with plants that mix in another grain, milo or sorghum. It does not contain any amount of appreciable oil to recover. It's fairly high fiber. So when that gets included in the feedstock mix, that additional fiber seems to interfere a little bit with oil recovery from our experience. In other words, if you have, say, 50% maize and 50% of the milo or other grain that doesn't have oil, your recovery isn't just 50% of what it was before. In most cases, it's slightly less. It's like the additional fiber from the other grain seems to interfere with oil recovery a little bit. So if you split it 50-50, you may expect your oil recovery to drop to say 40-45% of what it was on 100% maize. that's just what we've seen. But like I said, I don't really have any experience with the with rice being mixed. So with that, we will be having a booth at the FEW this year. Please join us. Please join us if you can, and stop by and see all the other AMS folks there. And Aditai will be there as well. We're planning some plant tours around the FEW to see some U.S. installations, hopefully within, not too far a distance from St. Louis. So with that, I thank you very much for your time. And any questions you guys might have, we'll try to field those.
So the session is now open for questions. If you have any, please proceed. So, sir, we have two questions in our chat box. And the first question is from Bula Mahato. And the question is, why not corn oil separated before fermentation?
That is a good question. That has been tried a couple of times here. I know of at least one technology that a company called ICM tried front-end oil separation prior to fermentation. The temperatures that they were using and the heat exchangers and things that they were using to try to extract the oil was scorching the starch. So they couldn't effectively extract the oil without damaging their starch. And then the damaged starch caused all sorts of problems in fermentation and then downstream of fermentation in drying and all that other stuff. So ideally, that is where, if I were running a plant, that is where I would want to extract the corn oil is before it goes into fermentation. We haven't seen a good technology here that can do that yet. There may be one on the horizon.
Sir, we have another question from the same person, Mr. Bhula. And the second question is, can rice will mix with corn?
Like I said, we don't have a lot of experience with rice here in the States for these applications. So I can't speak to it directly. I don't know if one of the Adita representatives has more information on that.
Yeah, Eric, sometimes like people, they do have like they don't mix rice and corn in the mill, but maybe they can run rice for a few hours and then run corn for a few hours. So they will have a mix of slurry in the fermenter. So definitely not in the milling, but in fermenter we might have
Yeah.
different proportions of a mix for and corn slurries.
So you're not audible.
I hope.
Yeah, now you're audible. Yeah, please continue, sir.
No, no, yeah, I was saying that the it could be a mix of corn and rice, but not in the mill, definitely. Some distillers might run rice for some time and then switch over to corn as per the grain availability with them. So the fermented slurry wash could be a mix of rice and corn, but not definitely in the mill.
Okay, sir. Thank you. The next question is from Mr. Amitabh Singh, and he's asking, what is the effect of demulsifier on mixed grain like maize mixed with rice?
Well, I can speak to the mixed grains that we use here, and the demulsifier it'll act on the oil that's in the maize and not really impact the other grains appreciably. I would assume it would be similar with the rice, since there's not really recoverable oil in the rice.
And the next question is from Manish Singh, and he's asking during demulsifier recovery 60 to 70%, how it is affected with increasing dissolved solid or with decreasing?
So we don't see that there's much impact on the dissolved solid with the demulsifier usage. Theoretically, there would be, because you're adding a chemical, which would then be measured as a dissolved solid in whatever process stream you're using. But if you're only in the range of, a couple of hundred parts per million, 10,000 parts per million is sort of a windage number for, 1%. So you're kind of in that noise of most dissolved solid measuring devices, whether that be a conductivity meter or a balance, like they call thermographic gravity analysis. And you weigh it wet and you weigh it dry kind of thing. If you're down in the 0.02% of that, then you're kind of in the noise of measurement, honestly. So it theoretically does impact the dissolved solids content, but not really measurably.
Okay, so the next question is from Mr. Shubham, and he is asking how liquefaction and fermentation enzyme impact on oil yield.
I think from our experience, we can see that the enzymes do have a major impact on oil recovery. That was one of the big three that we highlighted early on. Just in general, I can say that from what we've seen, the biggest impacting enzymes are the proteases and cellulases. And when I say impacting, I mean, we get a lot of experimental enzymes here in the United States, and they'll run one for a few months and we'll see maybe more oil available, maybe less oil available, depending upon the enzyme package. And that's for the enzyme companies to more or less optimize themselves, because the enzymes, especially the cellulases, can impact the viscosity of the various process streams. Viscosity seems to be a larger impact than even percent solids. I know at plant A, you could be running a 30% solid and it pours out of a beaker very, very easily, like water would. Plant B, running a different enzyme package, a 30% solid may hardly pour at all. It'll be like peanut butter or some other the thick substance. So I've been to plants where they're running an experimental enzyme package, and you grab your hot sample. If you don't do something with it right away, just the amount of cooling that takes place from the sample into the lab, you can hardly pour it out of a beaker. It's so thick. So that sort of stuff, when the enzymes are there accessing different parts of the starch and different grains, can have a big impact on the oil recovery downstream, from what we've seen.
The next question is from Mr. Eknath, and he's asking which is more suitable method of DCO separation, decanter or disc stack, in terms of oil recovery and cost effectiveness?
Very good question. So, like I said, there are pros and cons to each. As your plant, your particular facility evolves, you may evaluate different oil separation technology, which may fit your plant best. Like I said, the disc stacks are typically lower investment, upfront cost. They make a fine separation. The tricanters are typically, from what we've seen, a little more tolerant of a wider range of feed solids and viscosities. Higher viscosities tend to gum up the disc stacks a little bit, but you got to be careful with those. That's not necessarily an endorsement only for tricanters, because disc stacks work fine at many of our customers. So it really depends upon the needs of your particular facility, and as you add equipment, technology, enzyme packages, etc., your needs may change, right? So
The next question is from Mr. Sunil Rana, and he's asking after recovery of corn oil, DDGS price is less due to low oil content in DDGS. Please suggest it is viable in India.
I can say that here in the United States, the 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 price of the DDGS seems to be the price of the DDGS. We've had customers that have lowered their fat specifications multiple times due to being more efficient or moving oil. They still seem to get market price for their DDGS. That being said, there is some split market here for protein content seems to be the big divider here. Higher protein distillers grains can get a little more money than lower protein distillers grains. I'm not for sure about the India market, but here the oil content in the distillers grains doesn't seem to affect what you get, your market price for that product.
The next question is from Nishant Sharma. What is the best point of doses for demulsifier? Right before the transfer pump that transfer syrup to the separator or after that pump?
That I hate to be a little wish-washy on this, but that sort of depends upon your plant. So, and I've seen this at multiple plants and even all at the same plant where under one set of enzymes and feed and fermentation yeast and whatnot, the best point was injection point was right before the oil separating equipment, like probably 10 meters before the oil separation, no retention tank required. Then yeast and enzymes change over the course of a few years, and the best point goes back to where now they need more mixing and retention time. So they go back ahead of a pump into the suction of a pump and then before a retention tank to give it more time. So not to be wish-washy, but it really would be best if you could experiment with a couple of different spots in your plant. Doing those microscope analysis would also be helpful because if you can look at the undosed syrup or whole stillage, whatever your spent wash, whatever you're looking at prior to chemical injection, and you see nice big oil droplets, and then after a pump, they're broke up into nice small oil droplets, then you may want to say, well, this pump is breaking up my stuff. I may want to dose after it to recoalesce the oil. So you need to experiment a little bit. It's a good thing if you have a process engineer, you stick them on this and let them map out the potentially best way to do it. Because I've seen it in plants to where I can go and grab a dosed feed before a pump and a dosed feed after a pump and show the plant you're breaking your oil up. You're making these nice big droplets that the oil separator would like to get, and then this pump is really tearing them up, making them small. So you really need to sort of evaluate your own plant, see where the best place is ahead of your oil separators.
The next question is from Saurabh, and he's asking what is the major point in process control that affect in corn oil recovery and quality parameter of oil too.
The process point that most affects the quality of the oil? Is that the question?
Yeah, sir, I'm repeating it again. What are the major points in process control that affect in corn oil recovery and quality parameter of oil too?
I think the biggest thing that we see is just having good fermentation. You digest and ferment all of your digestible sugars to ethanol and then distill them out. Whatever it takes to get to do that seems to be the biggest impactor. Whenever people plants start having poor fermentation and they're not digesting all the fermentable sugars, dropping low ethanol yield, that seems to play havoc with the whole downstream system. But I think just good, complete fermentations is probably the best thing for oil recovery.
The next question is from Mr. Nishant, and he's asking how much retention does demulsifier require mixed with the feed before it enters the separator?
I would say similar to the injection point question, that this is a little bit, it depends. In general, more heat and retention are better. That is up until the point to where you make nice big oil droplets and then break them up again with another centrifugal pump. So again, I think you should evaluate for your own plant to kind of make sure. But just in general, the rule of thumb I think would be more heat and retention is typically better so long as you're not over emulsifying the product, the demulsifier and the oil.
Okay. And the next question is from Mr. Shankar Pandit. What is the ideal recovery of DCO practically can be achieved with respect to the total quality available in the mass?
Well, that depends a little on your injection point. If you're going to the spent wash, just post distillation, pre initial centrifuging into wet cake and thin stillage or centrate, there we're seeing yields here of 60 to 70% of the theoretical amount available. I think with some additional front end centrifuges that are more designed for oil extraction, that's getting up into about 75%, 80% of the theoretical oil available. That's where we are today in the state. A good application here gets over half, just somewhere around that 60% range of the oil available.
In the continuation, Mr. Shankar also wants to know the merits and demerits of demulsifiers.
The how much of the demulsifier?
Sir, merits and demerits of demulsifier. Merits and demerits.
Well, I of course think there are only merits.
Yeah.
But there is cost, so you would need to run your calculations to make sure that what you spend on your demulsifier is making you money. That's the big number that we run here. We're very attuned to making sure that we're not selling something that doesn't make our customers a positive cash flow. So that's what I would say about the Barrett. Because otherwise, as far as process impacts, we don't really see any. Doesn't seem to be any impact on drying or recirculation into the backset for fermentation or any of that. So pretty much just the cost equation. Are you making more than you're spending, kind of thing.
Okay, so next is Mr. Patla Suresh wants to know 200 KLPD corn oil separation equipment cost.
That you'll have to check with our friends at Aditya. They can get with you and do some specific cost and payback estimations for your particular plant. I can't just carte blanche give you a cost for 200. That would need a little more one-on-one discussion, I would think.
So this was the last question. Any other questions from the participant side? We have one more question in our chat box. And this question is from Mr. Ajay Sharma. And he's asking, can we use this oil for human consumption? These demulsifiers are for food grade NSF approved.
They are. They are, and we can provide documentation for that if so needed.
So any other questions from the participant side? So since there is no more questions from the participant side, let us conclude the webinar.
Thank you guys very much for your time.
Just give me some time.
Oh. Okay, are we done?
Yeah.
Oh, thank you.
Yeah, sir. So we are very thankful to Mr. Eric Yandell as a valuable knowledge partner. So, sir, please accept a token of appreciation from JIMA.
Thank you very much, everyone.
Thank you, everyone.
Really
Thank
appreciate
you
it.
all for your valuable time and participation. Good evening, everyone.
Good evening.
Good evening.
Bye-bye.
Thank you.